Okay, this is problem 2.4, and the objective is to find an equivalent spring that you could locate at point A that's equal to the same as these three springs that are located here. You can use the parallel and series spring formulas that come out of the book. Nothing wrong with that. I think and that's okay. I like to kind of go back to the fundamental concepts, and what I would do then is draw a free body diagram or write the equations of motion, either way, for this system with three springs, and then write it with one spring, and then say that the equations have to be equal. So anyway, bottom line, I want to write the equations of motion for this beam. To begin with that, I have to find out how many degree of freedom there is in this problem, and so I look for things that can move, and clearly the member OA can move. It can go rotated clockwise or counterclockwise. The book wants to use the variable z, so I'll use z to represent that. Up will be positive, and there's a simple relationship between the motion at the bottom of spring K3, for example, and it'll be 2/3 of z, which for small angles, essentially that comes out to a sine relationship. So anyway, we'll start with that. So that's 1 degree of freedom because of the beam. If you stop the beam from moving, then there's still a motion, which is the junction between K1 and K2. So what I'll do is I'll define a variable for that one that goes like this. So there will be, and I'll measure it off of static equilibrium. When I say up is positive, and we're going to call that variable y. Okay, so what I know is that there are 2 degrees of freedom, and okay, so it's 2 degrees of freedom, and I'm going to be using the 2 variables z and y. Because of the 2 degrees of freedom, I'm expecting to get 2 equations. So what I'll do is write or draw the free body diagram of the rod first of all, and so in that case, I'll draw the rod. And of course, because of the pin joint, you have forces back here. I'm not going to worry about those too much because I'm going to sum moments around the point O, and those have disappeared. Okay, so the first thing I've got is, we'll take the easy one first. I'm going to have a K3. So I write or draw the line for it, and I write an equation for that. So it'll be K3 times the deformation in the spring, which is the deformation under K3, which is 2/3 of the distance z. Now to get the arrow, I imagine that z is positive. If z is positive, it goes up, and I push on the spring K3. If I push on it, it pushes on me, and so it's pushing me. So the arrow goes down. Now let's get the other force, which is coming from K1. So I'm going to draw an arrow. And now I notice that the equation for this guy is going to involve both z and y. So I'm going to write K1, and I'm going to write z and y. And what I have to decide is whether z should be subtracted from y or should it be added. And to get a good idea about this, I will need well, excuse me, that's not z. It should be 1/3 of z. So I'll divide by 3. Okay. Now it's either a plus or a minus with this. So what I do is I imagine that z over 3 and y are both exactly the same values. And if that's the case, then the bottom of the spring goes up and the top of the spring goes up the same amount. So motion of both objects should produce no deflection of the spring. So if I add these two, I will be getting a non-zero value. But if I subtract them and they happen to be the same, I'll get 0, which corresponds to what happens to the spring. So I can conclude that I should be subtracting these. The next, and of course it makes no difference whether you choose z minus y or y minus z, because the next step is to imagine that the thing in parentheses is positive. If it's positive, then z over 3 has moved further than y. And if I move further on the bottom, I'm squashing the spring. If I squash the spring, I'm pushing it. If I push it, it pushes me, and so therefore the spring force goes down because it's a push. So those are the only forces that are acting on this guy. Now, what I'm going to do to get the other equation is simply write a free body diagram of the node between K1 and K2. So to do that, I draw a little dot, and that's my object. K1 is touching me, so I'm going to draw the line, write the equation for it, and then I pretend that z is bigger than y, or z over 3 is bigger than y, in which case the spring K1 is compressed. I pushed it. If I'm pushing it, it's pushing me, and so push is this direction, so he's pushing on that node point. If you notice, this force is equal and opposite to the one before up here. So those are equal and opposite, as Newton's third law says it should be. The node point is also being touched by the spring K2. So to get him, I draw the line. I write an equation for it. So this is going to be K2 times the only motion that's important is y. And now I imagine that if y is positive, I am pushing the spring. If I'm pushing the spring pushes me, and so this force is down. Alright, so now that I have the two free body diagrams, what I'm going to do is sum the forces. In the case of the beam, I'm going to sum moments. So if I sum moments around O, I get K1 z over 3 minus y, which is the force, and then I need to multiply by the moment arm, which is L. Okay, now this is producing a a moment in the clockwise direction, and since z is positive up, that's counterclockwise, this would be a negative moment. So I need a negative on this one. Now the other force that I have is from the K3. It also produces a negative moment. So it would be a negative K3 2/3 of z. And this is equal to moment of inertia times theta double dot. Alright, now for the other equation, what I'm going to do is sum forces. So up is positive, so what I have is a minus K2 y plus K1 z over 3 minus y. And that equals, the mass happens to be 0 because there's no mass or anything there, so the mass is 0 times the acceleration, so that gives me 0. Now if you look, there are 3 motion variables: y, z, and theta. Of course, theta is related to z fairly easily using small angles. It would be 3L times theta is equal to the value of z. So there's a relationship between the theta and the z. That gets rid of one of the variables. So now I'm left with 2 motion variables and 2 degrees of freedom, so everything should match up just fine. So what I want to do then is eliminate the variable y. So I'm going to take the second equation and I'm going to solve for y. Okay, if you solve the second equation for y, you find the following. You find that y equals k1 z divided by 3 k1 plus k2. Okay, now what I'm going to do is simply substitute the value of y into the first equation.